Hey guys, it's probably going to be a bit of a longer video here. I just want to make a demo here about why it's so important to have PWM control on your motors. If you're looking for over unity results, I'm not saying you can't get it though, just by putting all the power into the rotor and spinning it like that, getting your mechanical energy out of the rotor. I'll show both in this video. First part's going to be just pulsing it. So the voltage is going to be on that scope over there where my hand's pointing. You'll see the top is the input. The spikes on the top will be the input, and it's going to be coming from this battery right here, which is like 13 volts or so. I haven't even checked it. Where did I put the meter? Here we go. I never even checked it. I just grabbed it off the shelf. So let's put this over here. Take a quick reading here. Right now, 13.3. So it says somewhere around 13.6 on the scope. But it catches the dirty energy too on the scope. So then the blue one here is going to be the input coming out of the battery, out of the 12 volt battery. So anything below the line is what's coming out of the motor, or out of the battery going into the motor. And on this bottom line is the output, which is going into this 57 volt battery bank right here. It's at 57.55, that's the voltage of it. So anything that's below the line is going to be what's going into the battery bank for current. Each of these settings are going to be at every 10 millivolts. It's on the 10 millivolt for here, for this right here. Each one of those is 10 millivolts. So every one of those is 10 milliamps for both. You can see they're both set for on the 10 millivolt scale. So I'm going to turn these on. They drift a bit, so I'll be adjusting them as the motor's running. And here is going to be the frequency up here, these smaller numbers. And they're just measuring this coil right here. There's the AC voltage of that coil and the frequency. And you can get the RPMs by that, just by dividing it by 5 and multiplying it by 60. That's so many RPMs. So start the motor. Here will be the voltage of this battery. Which way does it go? Oh, it is. Okay, so you can see that's the bottom. Below the line is what's going into the motor. And this is going into the output battery bank at 57 volts, 57.55. And you see the top above the middle line there, the top is the input coming out of the battery, and the bottom of the back is the back spikes going into the output battery. I can adjust it from here to fine tune the motor. I haven't had it running, so I don't know how it's tuned. It's been, I don't know, it's been quite a while since my last videos about this. It's been on the shelf. drop some. There, got it adjusted. Okay, so right now I can measure this here. This bottom here, the average. See, 9. Millivolts down to here, and each millivolt is 10 milliamps. So you're looking at 90 milliamp pulses, 94 milliamp pulses. And go to the top one. So around 180 millivolt, 118 millivolts, so about 180 milliamps is what you're seeing here for pulses. Down to the bottom here. Well, an average I took, I didn't go right to the bottom. So the input voltage is 13.3 volts. Times 0.18. Looking at 2.4 watts on the input. And the output is 57.55 times 0.09. Looking at 5.17 watts on the output. And that's just like a quick measurement, like, without any tuning at all here. I've just turned the motor on. You know, I can get the motor to go faster or whatever. I think it's trying to go to 5.6 there on this. So let me just get rid of the, and like you can see the PWM, what it does. So what you need to do with this type of a circuit is, when you're trying to get over unity out of a pulse motor, you need to pulse it on quick, like very quick, so the current can't follow. You just want to pulse it, turn it off, get your back spike, pulse it, turn it off as fast as you can. It all depend on your motor too, like the spacing of your magnets and stuff like that. And like here, I'm going to adjust this, and you can see the difference it makes on your timing and speed. You know, like, makes a huge difference just by moving it a tiny little bit, moving it away from the motor. Like, there's a reason why I use Hall effects. See here, it's not like I don't have optocouplers. I got plenty of those. There's a reason why I don't use them for pulse motors. It's because it's incredibly hard to time your motor with them. You need to have a timing circuit that can do a PWM pulse into your motor. And some that's not crazy complicated. Don't use a gate driver That's something you don't want to use. Like this circuit takes less than 10 milliamps of the input power to run it. So let's just get rid of the pulse width completely and watch the difference. You see any current going into the battery? There's a little bit there. You can see the back spike is there, the current. Let me just adjust this so it's, you can see it's just below here. But look how much is coming out of the motor. And this isn't time for any speed here either. If I adjust this, you'll see the difference. See, like, look at the huge difference this makes. Let me just get rid of this here, so I'll just put it up so you can actually see it. So now the top is at 50 millivolt settings and the bottom is at 20. So that's the current from the back spike going into the output battery. But look at the current that's going into the motor. Like, look how wide that is. You know, there's still current going into the battery on the output, but it's not over unity. Not with how wide this is. And that's why your coils will get hot. Is because your pulse duration is too long. See, I have 0 duty cycle. It's like right to the top. Duty cycles, 100%. See the difference? Now let me turn this down. See, now I'm putting a pulse back into it as it fires. It'll take a while for the motor to slow down and stuff again before it starts to come back. And I'll have to tune it a bit. It always works best right from the stop. But it'll come back. And you'll see that the output is greater than the input by doing this. Like, this is 57 volts battery. This is only 13. Where the current is coming out of. And this can be tuned to be a lot better than this. This is just quickly pulling it out and showing you guys. And this isn't without one of these coils reversed either. This is just the plain motor running with these coils in series. One driver circuit. I'm also going to be showing a driver circuit that flips the poles of the motor. It'll run both sides, both magnets on the rotor from one. See, like there now, look at the difference this has made. Just the way it's running there now, look at the output difference. This is way different. Sometimes that's what you have to do also with your motors to get these type of results, is get it past, speed it up and let it slow down. on its own. As you, like if we measure this now here, pause this. See, now it's at, oh yeah, okay, I'm wrong here. I just gotta put this back to 20, 10. Yeah, there. But still, you could still take these measurements. And I get the in this 10 millivolt setting, everything's a little more finicky with the drift on those meters because it's a really fine setting. Pause that. Go like an average here. Looking at 17 on the input, so 170 milliamps. And an average here, it's about the same, around 9 milliamps, 90 milliamps. So it's about the same. And that was after me affecting it. So if I change this here, you can see how much it moves it. Changes the whole motor. That's why the Hall effect is the most important thing to have for timing. So watch this here. I'll put a bigger battery in front here, right here. Let's just change this out with a 24 volt battery. And this is the battery that comes off of my other circuit for the solid state. It hasn't been charged conventionally at all. It's always been on that. I don't know what the voltage is. Check that right now. It's always full. .44. Start this up. This thing's going to draw some current probably. So he wants to go. Let's just see how fast we can make this work. Look how much of not over unity it is. Because now you're forcing the power into the coils at a much higher voltage. But you always want with your coils is a low resistance in your coils. See, you wouldn't even be able to get over unity with this setup right now. Not without raising the output voltage. It has to be higher than that to be able to get over unity. So you want your coils to run on a low voltage, as low as possible, with a high voltage on the output. To get a 1-to-1 ratio is really hard. So let's just see how it affects the motor. Let's just crank this thing up and see how many RPMs we can get out of it, and see how inefficient it becomes. I'm gonna have to move these to a higher setting. put them both equal. They're both at the 50 millivolt setting. You can't even see it at all. No power coming out on the output now. Because now you're forcing it into the battery. Or into the motor. The coils are just, they're gonna just get hot. But you got insane amounts of torque on the motor itself though. So this is just like a normal motor, like as if you're just pulsing it on and off. You know, it can lower the duty cycle. And the frequency with this circuit. This is just a really quick off and on pulse. You can still see the back spike, but there's no current behind it. Nothing. If I lower this a little bit, make it a little more sensitive, you might be able to see some. But it's really small. So let's just get this thing where it wants to go. So we're at 250 hertz and climbing. And another important thing too is to be able to adjust your coils while it's running. See how sensitive it is to timing? I've built, I don't know, probably 50 pulse motors, and it's always like that. Big and small. I know at this voltage that it'll run itself till it blows up. That's 300 hertz. And that's only with half the motor being used. But look at how inefficient it is. There's no power coming out of it into the output batteries. Around one of these coils here and see. Just gonna reverse the polarity on this coil. It's back on now. See, like, that's a lot of current going in there. Let's just measure that. .4 millivolts, so it's over an amp at 26 volts, and there's nothing coming out. See, and by reversing that, it slowed it down. Should be able to get it to where it wants to go faster though, just by moving the coils. There we go. See how much of a difference that makes? When you don't have this built into your motor, you just don't know. Like, look what this does. See how the current dropped and the speed of the motor is going up? If you don't have that built into your motor, you're not gonna succeed. It looks like shit, but look how it works. Set 380 hertz. You know, at 400 hertz, it's probably over 5,000 RPMs. And it's just gonna go till it blows itself out. It will destroy itself if I don't stop the power here. So 425 hertz, I'm turning it down, because I don't want it to blow up and shrapnel everything around here. Let's just see how many RPMs that was. Well, what did I say? 425 divided by 5 times 60. 5,100 RPMs. So, you know, it probably would have doubled that. That's, you get into that point, then you can start using it as a mechanical advantage. But there is no over unity unless you try to collect it off the rotor itself, which is even harder than doing it with the back spike. You can see. It's definitely not going to be showing extra output like this. That's why it's so important to use a pulse width. But I just wanted to show that and do a quick video about it. hopefully that helps some people out about understanding how it works. Because it's not just about pulsing one pulse in per magnet and letting it back spike. It doesn't work like that. Like even Joe's motor, Newman's motor, he pulsed it numerous times on each 180 degrees. And then the pole reversed and he did it again like that. It wasn't just on and off. But thanks for watching, guys. Hopefully you enjoyed it.